So today I'm going to talk to you about CCUS. I'll give you an overview of the process, the fluids, and why we need accurate flow measurement of CO2 and how we can achieve that. So what is CCUS? I'd like to start with a simple overview of the question because I don't know your experience, I don't know your understanding of the issue, so it's good to give an overview before we get into the details. CCUS stands for Carbon Capture, Utilisation and Storage, and is a process of capturing CO2 which would otherwise be emitted and then transporting it over long distances to be either utilised or permanently stored. So why are we doing this? Ultimately, as we know, we're emitting too much CO2, which is leading to an increase in global temperatures. As part of the report on the mitigation of climate change, the IPCC have stated that CCUS is a key technology in our fight against climate change. As a result, many governments are stepping up to this challenge, and the UK government have put £1 billion into 2 CCUS clusters, which are due to be in operation in the coming years, and more clusters to be online by 2030. CCUS is there essentially to buy us more time and to assist in those industries that are very difficult to decarbonise. The process works by capturing the CO2, which would otherwise be emitted through the chimney stacks, and compressing it into a high pressure gas or a high pressure liquid. Typically, these capture plants are taken from industrial sources, which have higher emissions, leading to an easier capture when compared to having many small emission sources, from example cars and homes. So typically they'll come from, say, steel plants, power plants, cement plants, as we can see on screen here. Now, many of these industries are very difficult to decarbonise. They may have very high temperatures as part of the process, or the process leads to CO2 being emitted and therefore cannot be fully decarbonised. So CCUS will be key for these industries to manage in the long term. So in the UK and EU, CCUS is financially underpinned by the Emission Trading Scheme, along with other commercial contracts for the storage and licences. Essentially, this means that the emitters who capture their CO2 are paid via subsidies for per kilogram of CO2 they capture. This leads to quite an important question as to how do we quantify the amount of CO2 which they capture for these payments to take place. Well, the answer to this is much in the same way that the existing oil and gas infrastructure works, that we install custody transfer standard flow meters in these pipelines, which measure the CO2 transported between the capture plants and the storage or utilisation sites. It's important that we know how accurately these flow meters are reading. It is a requirement of the emission trading schemes to measure the CO2 for reporting purposes, and is often part of the contract. So it is very important that we do measure this. CO2 in the CCUS transport sector will be transported across the phase diagram, which you can see on screen, typically in one of 3 distinct areas. It may be transported as a high pressure gas, up to maybe 40 to 50 bar. It may then also be compressed further into sort of liquid form or dense phase, which is a term I'll come to explain later. And it may also be cooled and compressed further for shipping transport. Now, from a purely thermodynamic point of view, there are only three fluid phases of matter. Gas and liquid we know about from day-to-day operation, but there's a third, which is supercritical, essentially meaning that the fluid is above its critical pressure and critical temperature. This is a complicated phase to work in, and to put simply, it's difficult, and a number of unusual things begin to happen. However, the industry is tending towards using a more sort of an industry-focused engineering term, which is referred to as dense phase. Now, the definition for this has not been fully harmonised, and on screen here we have two definitions that are commonly used. So you can see that the term dense phase covers the liquid, the thermodynamic liquid phase, and covers a portion or all of the supercritical phase, depending on how you define it. So it's worth bearing in mind when talking about dense phase that as a fluid, sometimes this can be a supercritical fluid and can lead to further challenges in the measurement of this. So what are the challenges facing deployment of CCUS, certainly from a measurement side? Well, for the regulations and contractual framework to be successful, as we mentioned, we need robust flow measurement of liquid and dense phase CO2. Typically, from experience or experience of existing sectors, this is completed using calibration of the flow meters in a fluid which is as close to the live fluid as possible. This allows us to validate these meters and ensure that they are performing within the stated measurement uncertainty. Now, for the UK and EU emission trading schemes, that measurement uncertainty is 2.5% by mass flow of the CO2 part of the flow. Some of the commercial contracts in place may have a tighter uncertainty requirement. So calibration of these meters is really quite important to make sure we meet this. So it's worth noting that the CO2 pipelines, certainly in the UK, are expected to reach up to 23 megatons per year by the year 2035. So if we're going to calibrate these meters, initially we'd look to use CO2 as our calibration fluid, but that poses quite a difficult question, or quite a difficult issue, in that there are very few calibration facilities, certainly accredited calibration facilities in the world, and none of these facilities are able to match these flow rates that we mentioned. On screen here we can see the three accredited labs that we're aware of that cover the gas phase. There's Fortis BC in Canada, DNV in the Netherlands, and ourselves here in East Kilbride. And although we have a slightly higher flow rate than our competitors, we're still a good chunk behind the industry requirement. If we look to the liquid and dense phase section, the issue is even worse. There are currently no facilities anywhere in the world that are accredited for use for calibration of liquid or dense phase CO2. There is IFE in Norway that has a liquid CO2 flow facility, but is not accredited under the ISO 17025. We are currently designing and constructing a facility, a small 2-3 inch facility. But again, it's unlikely to, it will not cover the main flow rates. So how do we get around this? We need to calibrate these flow meters to meet the regulations and the contracts, but the facilities aren't currently there. Well, the next thing we would do is look to use another fluid. This is an approach that is common practice in other industries. And my colleague Chris Mills did a brilliant webinar a few weeks ago on this exact topic. In that, he mentioned that with existing oil and gas and other infrastructures, we already use alternative fluids as our calibration medium. Calibration laboratories can't hold every single live fluid that we need, and therefore we hold a select fluid and match what's closest to your requirements. And this works, and there's plenty of data to show that this works in water and oil and gas sectors for this. But we don't know whether this will work for CO2. We've mentioned that CO2 already is a difficult fluid. It's got its own challenges. So we don't really know yet whether this will, whether we can use another fluid and transfer the calibration. So this is part of the question that I've been working on over the last year or so. And to answer this, we've done a series of experimental campaigns, research experimental campaigns. It started with us building a transfer package of several flow meters, 5 different flow meters. We've calibrated these meters in our own water calibration facility. We then apply the calibration to these meters for the future tests. We then tested these meters again in our oil facility or at an elevated pressure and temperature, where this allowed us to validate the water calibration and also test for any pressure effects and temperature effects on these meters. We then shipped all these meters out to IFE in Norway and tested them in liquid and dense phase CO2. After this, we analysed the data and assessed the transferability of that water calibration to CO2. So this transfer package that we mentioned included 5 different flow meters across 4 different metering technologies. Metering technologies were chosen to sort of emulate what we'd likely see in industry, in the industry. So on screen on the drawing, we can see we've got an orifice plate, a 0.6 beta ISO compliant orifice plate. Downstream of that, we then had 2 clamp-on ultrasonic meters supplied by Flexon. Downstream of that, we had a helical turbine meter from OGM, and downstream of that, a 1-inch Emerson Coriolis meter. Now today I'm going to present some of the data from the Coriolis meter. The data from the other meters are due to be are in a journal article which has been submitted for peer review, so hopefully fairly soon I should be able to report on that information. To complete these flow meter measurements, a number of other measurements were taken, including pressure and temperature. The orifice package also requires the measurement of the differential pressure. And in this case, that was done with a range of differential pressure transmitters, each calibrated over a small range to allow for greater accuracy. And then together as a group of transmitters, they cover the range of pressures that we expected to see. It's worth remembering here that there is no traceable reference for CO2. in the liquid phase, and therefore that meant that we needed to use the orifice meter as the reference and do a relative comparison between the orifice meter and the other flow meters. Between testing at NEL and at IFE, the package and the orientation and pipework all remained the same. So if we think back to the experimental process slides, the first step was to carry out a calibration in our water facility. We started off by calibrating the orifice meter. This was done by using an offset to the ISO 5167 discharge coefficient. The resulting measured discharge coefficient in oil, water and gas was within 0.2% of that fitted discharge coefficient. And this orifice meter, as mentioned, with this discharge coefficient was used as the reference in the following tests. We then calibrated the 1-inch Coriolis meter in water and applied a corrected K factor to the pulse output of the meter. The meter is calibrated over 1.2 to 6 kilograms a second. And the resulting discrepancy between the orifice meter and the Coriolis after the calibration was applied was then plus or minus 0.06%, which is a very good result and allows us to use this as a baseline to compare the CO2 results against. So after the water calibration was complete, we took it to our EPAT facility and validated these results. We were also able to do a pressure correction and an offset for process pressure effects. And the resulting error at 20 and 30 degrees in oil was within plus or minus 0.08%, with the exception of one group of flow rates at 20 degrees at the bottom there. Now, for reasons that will become apparent in the upcoming slides, we then also calibrated this meter in our densitometer facility and provided an offset across a range of pressures, temperatures and densities. For this, we were able to take the error from 3% down to within plus or minus 0.01% or less. So once this testing in East Kilbride was complete, we packed everything up and took it out to IFE in Norway to complete the testing in liquid and dense phase CO2. The test setup at IFE is on screen here. You can see the orifice meters and then the other meters downstream of that, and the Coriolis, which I'm reporting on, is just out of shot. When we tested these meters in liquid CO2, we chose 4 distinct fluid conditions, pressures and temperatures. These pressures and temperatures were chosen to emulate pressure conditions that are likely to be experienced in CO2 transport. So largely, as you can see, they're covering the dense phase pipeline region and also one group of points covering the shipping transport area to give a good coverage of these results. Now, it's worth remembering, and I make no apology for repeating myself on this, that there are no traceable reference meters for liquid CO2 at IFE or anywhere in the world. So for these tests, we completed a relative comparison between the orifice meter and the Coriolis meter. Now, for us to complete this relative comparison of these meters, a number of other measurements are needed and other quantities are required. As we know, orifice meters require, among other things, knowledge of the static pressure, the differential pressure, the temperatures, and importantly, the density of the fluid that you're measuring. This density can come from largely one of two sources. You can either measure the density directly using, say for example, a densitometer or a Coriolis meter. Or you can take your density from an equation of state. So the first group of results I'm going to show, we have taken the density measurement from the Coriolis meter, applied that calibration from a few slides ago, and used that within the orifice mass flow calculation. And from there, developed our results. So on screen here, we have the results from that 1-inch Coriolis meter. In the blue and the brown squares, we can see the water and the oil results, which provide that baseline that we're comparing the CO2 results to. And in the coloured triangles are the results in CO2. Overall, the agreement between the 2 meters is within plus or minus 0.35%, which is good. There is a slight positive bias, which we can make out across the fluid conditions. It's worth noting, though, that this positive bias and agreement is within the uncertainty of this orifice meter. Now, thinking back to the source of density, we'll now look at the results when the density used in the orifice mass flow equation comes from the Span-Wagner equation of state for pure CO2. It's worth noting here that there have been no other changes in the results, and what we're going to show is just the source of density here. So here on screen, the same set of results as before. You can see the baseline water and oil results, and then in the coloured triangles are the CO2 results. Again, there's still a positive bias for the liquid phase of CO2. Slightly larger, the error is within plus or minus 0.4% this time. But what's most noticeable is that there's a substantial shift in the results for the dense phase at 40 degrees. Now that region is within the supercritical region, the sort of thermodynamic supercritical region, and it shows you a significant change. But it's worth noting here that we have to look at these results in relation to where they're going to be used, and these results will be used in relation to the UK and EU emissions trading schemes, which have a required uncertainty of 2.5% in mass flow. So if we look at those results with the y-axis opened out to see those 2.5% uncertainty bands, you can still, if you look very closely, make out the bias from both results. But it's very small. It's very small in comparison to that 2.5% uncertainty band. So what conclusions can we draw from this? This piece of work is, we believe, is the first set of results of its kind to be presented, and therefore is really significant. The work presents a relative comparison between an orifice and a Coriolis meter, which was tested in water, oil, liquid and dense phase CO2. The baseline discrepancy between the 2 meters in water and oil was plus or minus 0.08%. The results in CO2 thankfully suggest that the calibration of a Coriolis meter with water can be extended to liquid and dense phase CO2 with an associated uncertainty of approximately 0.35%. It's worth noting here that 0.35% is approximately within the uncertainty of this orifice meter. And to further understand where this comes from, we need to do more work in the future, which I'll come to talk about later. So that's liquid CO2. That's calibration transferability for liquid CO2. It's definitely a difficult fluid. But we've also done some work in the gas phase. We recently completed upgrades of our high pressure gas facility. So it can now take nitrogen and CO2 and provide calibration of meters in both of those fluids. So as part of a project, a European project called the Metrology for Decarbonising the Gas Grid, or decarb, we did some testing of a range of flow meters. We had a turbine meter, an orifice, a Coriolis meter, and an ultrasonic meter. And today I'm going to present some of the information, some of the data on that Coriolis meter. So we first of all calibrated the Coriolis meter in nitrogen at 10, 35 and 60 bar, provided an offset to the meter, and then tested the meter in CO2 at 27 and 37 bar. Now these pressures in CO2 were chosen largely because at 27 bar the density of CO2 is very similar to that of nitrogen at 60 bar. So on paper is quite comparable. And we can see here on screen that there is no notable offset in the results, no noticeable bias, which is very positive. If we then look at the results again in relation to the emission trading scheme requirements, the results look very good. It's a very positive result. But this is just one set of results. This is just one laboratory. To follow the scientific approach as such, we need a consensus across many independent bodies and many meter sizes and pressures and fluids. And we're in a better place for that with gas flow measurement. There's a small scale primary gravimetric standard at the Heriot-Watt University, again tested as part of the same project, and they've tested a small Coriolis meter in nitrogen and in CO2 and come to the same conclusions, that there is no discernible offset in the results. DNV in the Netherlands have also completed results. They've tested in CO2 and I believe natural gas, and again shown no notable change in the results. At Fortis BC in Canada, as part of a joint industry project, they've tested in natural gas and in CO2, gas CO2, with a Coriolis meter, and shown no change in the results. These meters and these different these tests and projects were done across different sizes of Coriolis meters and different manufacturers, which is an important consideration. So what does this tell us? We have 4 different laboratories, 3 different meter sizes, showing largely similar results, which is brilliant because that shows or suggests that a Coriolis meter can be calibrated with an alternative fluid, whether that's nitrogen or natural gas, and be used with gas CO2. So where's our next challenges? We've completed this testing in liquid CO2 using pure CO2. But in reality, in the CCS pipeline streams, the CO2 will not be pure. Ideal combustion, the results will be CO2 and water. But no process is completely 100% efficient, and therefore there will be impurities, post-combustion impurities or other impurities from whatever process the CO2 has been captured for. And these can include, among other things, oxygen, methane, nitrogen, argon, carbon monoxide, as well as NOx and SOx, which we here mentioned. This begs a large question of what is the effect of these impurities on our flow measurement. Apologies. And what other challenges come from these? Now, if we go back a few steps and look at the phase diagram for pure CO2, we can see the gas phase, the liquid phase, and the supercritical phase that we'd mentioned before. Now, on that line between the gas phase and the liquid phase is the liquid vapor boundary. And essentially what that means is that if you choose a pressure and a temperature that points you exactly on that red line, then CO2 can exist in equilibrium in both the liquid phase and the gas phase. Much in the same way that a glass of water will have liquid water at the bottom and there'll be some water vapor above the surface. Liquid CO2 anywhere on that line can exist in what we refer to as a two-phase region, which is essentially how the shipping transport works, similar to current LNG transport. If you move slightly up in pressure, all that CO2 will condense into liquid CO2, and you will only have a single phase. If you drop below that line, drop your pressure, all of that liquid CO2 will evaporate, for a word to say, and become gas CO2. When we include impurities, some really strange things begin to happen. With only 5% nitrogen added to the CO2 stream, that line where the two phases can coexist opens up into a whole two-phase region. In this case, with nitrogen and just CO2, that two-phase region can be as wide as 30 to 40 bar, and cause other changes in where that boundary sits. Now, the biggest challenge that this poses to the industry is that if you are using the equation of state, so you're measuring your pressure and you're measuring your temperature at a site, expecting to have pure CO2, then you may think that you are sitting in the liquid phase and have a density of a certain quantity. But because of the addition of impurities, you may actually be in that two-phase region. Now, for some areas of pipeline flow, that might not be an issue, but when it comes to flow measurement, two-phase flow is certainly more challenging than single-phase flow, and is certainly not ideal when you've calibrated the meter for single-phase flow. So, generally speaking, you'll try and avoid being in a potential two-phase region, partly by knowing the composition of CO2, but also making sure that your operating pressure and temperature at your metering station will be out with that region. So then the next point is well, what effect does that have on the measurement of CO2? And we don't really know. We've done some research into pure CO2, which I've showed in the slides before, but there's very little work in impurities, or published work in flow measurement with impurities. As part of the project with the small scale facility at Heriot-Watt University, they have done some tests with CO2 mixtures and given some preliminary results on the matter with a small scale Coriolis meter. This shows suggests that that there is no significant change, but we will need to do more work in the coming years to really ensure that this is the same across all meter sizes, across all mixtures, realistic mixtures and pressures and temperatures that we're likely to see. So, as mentioned, the results from that preliminary small-scale testing on the Coriolis meter suggest no significant shift in the results, but we need to do more work. As part of a project called NCASE, which is a European-wide project which looks to improve the sort of collective knowledge and the abilities of the research infrastructures around Europe for CCUS, TÜVSÜD at the National Engineering Laboratory have received funding to build a primary standard for liquid and dense phase CO2 flow. And this facility we're currently designing and building with a view to having this ready for operation by next year. This facility is really quite exciting and will provide us with a lot of data to answer these questions, which I'm leaving hanging in this webinar. We'll be able to test up to 200 bar, up to 50 degrees Celsius. And most importantly, we'll be able to test with mixtures of CO2. We'll be able to custom mix our CO2 stream as we see fit, as we need for the needs of the test. So that'll be something to watch out for, and hopefully I'll be coming back in the, next year to provide some information on the results of that. So thanks for listening so far, and I'd like to just introduce the Global Flow Measurement Workshop, which is a fantastic workshop which is run jointly by ourselves and Tekna in Norway. We will be hosting it this year in Aberdeen in October, and registration for the event is open. It's a fantastic opportunity to come and see presentations on the latest technologies and new happenings within the flow measurement industry. So thank you very much for listening, and I'm more than happy to answer any of your questions.
Thanks for that, Russell. Before we go through some questions, I believe a few of you have been experiencing some technical difficulties with the video feed. Apologies for that. We will be sending you a recording of today's webinar, so that shouldn't be affected by lag or any connection issues, and we'll also be sending you a copy of the slide deck. So hopefully that will cover the bits that you missed. Okay, Russell, we'll just dip in. We've got a few questions here. Let's kick off with, what's the likely cause of the difference in the liquid CO2 results between the measured and equation of state density?
Okay, yeah, very, very interesting question. If you just allow me to flick back a few slides, and I will show that. So if we think back to these results here. So when we looked at the so this is our tests between water and liquid CO2, and when we measured the density directly and used that density for the reference orifice equation, we got these results on screen. And then when we used the equation of state density, as I mentioned, the results at the supercritical region moved quite significantly. This is certainly something that we had us scratching our heads for a while, and essentially comes down to two potential causes of this. One is the CO2 that we tested and had a purity of about 99.8%, I believe. So small trace amounts of impurities. And the equation of state that was used was for pure CO2. So there's a possibility that the small trace amounts of impurity in the CO2 can lead to inaccuracies within that. The other possible cause is that in the supercritical region, the density is very sensitive to changes in pressure and temperature. So a small change in your pressure, a small change in your temperature results in a much, much larger change in your density when compared to other regions, whether it's in the gas region or in the liquid regions. Now, we completed an uncertainty budget for this test and put in some terms to cover potential inaccuracies in the equation of states because of impurities. But the largest, or one of the largest sources on uncertainty came down to pressure and temperature in this region. So we think this is most likely to be the cause of this substantial shift, is the uncertainty in your pressure and temperature measurement causing, leading to larger changes in that density measurement.
Okay, yep. Okay, what effect, if any, do you think there will be on flow measurement with the addition of impurities to liquid, in a liquid CO2 stream?
So it's a difficult one to answer just now because there's not been a lot of work done on that. The biggest challenge is, or one of the larger challenges that we know of is understanding the fluid properties and understanding the effects of these impurities on the fluid properties, like the density, the speed of sound, the viscosity, and ensuring that we have accurate data to provide this. As far as the raw measurements, whether it's the Coriolis meters or ultrasonics or turbines, we don't really know. We have that data from the rig at Heriot-Watt University, which is promising for a Coriolis meter, but we'll need to do more work in the coming years to really understand what the effects are.
Yeah. Okay. Next question. Even when the density, hang on, there we go. Even when the density is measured directly, some of the fluid properties will need to come from the equation of state. Could this have an effect on the test results?
So as part of the orifice calculations, there's a number of other fluid properties that are included within that. And because in the test situation we can't measure those directly, we have to take those from the equation of state. So again, taking your pressure point, your temperature, and working a value from there. So there is sources of uncertainty in the results from there. However, from completing the uncertainty budget for this test, it showed to be a very small contribution, very much a negligible contribution when compared to, for example, density and other components.
Yep. Okay. There's a load of new questions come in. I'm just trying to digest them as we speak. Is there any reports available on any of the research that we've done so far? I know this is very much work in progress, but is there any reports available for people to read right now?
Yes. So I presented. So the results on screen I presented at the Global Flow Measurement Workshop back in October. So there's my conference paper on that. As far as other reports, as I say, the rest of the results, so the other meters in the tests that I haven't reported on today, they will be reported in a journal paper, which has been submitted for review, and hopefully in the coming months will be available for people to access. So that's largely what's available just now. I imagine in the coming months and in years there'll be a lot more information coming out.
Yeah, it's very much work in progress at the moment, isn't it?
Yeah.
Which correction factors were applied to the Coriolis meter? Has any correction for speed of sound effect been applied? And this is for the gas phase measurements.
The gas phase. So the Coriolis meter, we trying to think back. So in the gas phase, it was calibrated at pressure, and I believe, I'm trying to think back and scratch my memory here, I believe we just offset for the pressure effect. I can check and answer.
That's fine. That's one we'll follow up on after today's presentation with that information. Sorry for putting you on the spot there, Russell, with that one. Let's see. What's the uncertainty of the gravimetric rig, or the gravimetric lab? Sorry.
Gravimetric lab. That's also one I'm not quite sure off the top of my head. I would need to find out. That's this one.
Right. I'm just looking through, see if there's any more we can answer right now, and I think that's probably about it for now. There are a few questions on there that we'll probably need to follow up with you on, get a little bit more information as to what you're referring. So if you've asked a question and we haven't covered it yet, don't worry, we will pick up on that and we'll get back to you. Okay. As I mentioned earlier, you will receive a link to recording for today's presentation. Please get in touch with us and let us know if there's any webinar subjects you would like to cover. It's great to hear exactly what you're interested in, so feel free to get in touch with us. You can contact us on info.uk@tuvsud.com. Feel free to visit our website, www.tuvsud.com/UK, for more information. Just to reinforce what Russell said, the Global Flow Measurement Workshop is going to be a source for a lot of this, the findings for projects like this. You can see from today's presentation, it's very much work in progress. But you should be confident that we're actually working together with labs across the world to answer some of the questions that we don't yet have answers to. So, look online, you'll get the information for the global workshop, but we definitely reinforce what Russell said and make sure that you come along to that this year in Aberdeen. On behalf of myself and Russell, thanks for taking the time to join us today, and enjoy the rest of your day. Thank you.